All right, so yeah, I'm going to be talking today about how to choose a logical replication system, specifically looking at Sloane and Picardo as two examples, which I've worked with both extensively, and they're both very good. But they have different things that kind of underlie them, different assumptions, and they're better in different cases. So just going to do kind of a brief overview of replication in general first, then look at Sloane specifically, Picardo specifically, take a look at some of the different comparisons, direct comparisons between them, and then have some specific cases that we've used both in different scenarios. And we'll go ahead and start off. Well, let me go ahead and save you time. If you're looking for a right choice or magic bullet, there's not one. You can go ahead and find a different class right now. It's just really a matter of understanding the constraints and applying engineering decisions. But yes, so replication in general. We use replication for many different things. There's, of course, disaster recovery, high availability and failover. If you want to have read and write scaling, backups, there's all kinds of different scenarios that replication just in general is useful. One of the things we want to look at is the difference between logical and physical replication. Amazingly, now that Postgres has built-in replication, do we still need logical replication-based systems? And I think the answer is yes. Logical replication supports different hardware and major Postgres versions. You can choose specific databases or tables to replicate. And if you want a target database to be writable, that's something that is necessary. The built-in, like hot standby, does not allow you to write on the slave because it's actually the same data files. Looking specifically at physical replication, we have the high-level overview. That's what's known as the warm standby or hot standby. It's called physical replication because it's actually replicating the actual physical files on disk. Postgres's built-in replication, it's built on top of its recovery mechanism, and it's actually processing the WAL data, either WAL archive files or individual WAL records. And so that'll instruct the system to basically make the identical changes to the disk files. And so that's something that will then mean, just by virtue of this fact, that you're not going to be able to make changes on any of the standbys that are independent, because then the data wouldn't be consistent between the things. Some of the benefits of physical replication are that it is easy to set up and use. It's ideal if you're just looking for kind of a high availability failover or simple read scaling. And as of 9.1, it supports synchronous replication, which, if you are really concerned about durability, that's something that it will not commit on the master until it is verified that it is committed on the slave. And so you know for sure that when it's able to, say, apply this, it will have been applied, and you are guaranteed to never have lost that transaction. Of course, also, it changes, since it processes all changes on the database itself. It means all of the DDL changes, any of the tables that you create, indexes, that kind of thing, all of that is going to be propagated over to the standbys as well, and that's something that you don't have to manage yourself. Some of the limitations, though, of physical replication are you need to have pretty much the same hardware, at least the same processor architecture. You need to have the same Postgres version itself, and you, again, have the read-only standbys. There's no local changes at all on any databases in the cluster. That's something that you have to, basically, it's all or nothing. Every single change is replicated, even ones that you really don't care about, and that can cause just inefficient use of your resources, or makes it more difficult to basically get the things that you need. So we'll talk a little bit now about logical replication. At the high level, that's basically capturing and replicating any of the logical changes made to the database, and that's basically inserts, updates, deletes for the tables in question. Most logical replication systems, in fact all of them that I know of, work via triggers on the tables themselves that'll capture basically the information about the changes that are made, and they usually have a portion and where they have a daemon that basically manages the changes between clusters and applying those changes. And as such, it's inherently asynchronous. It's not going to be something that you can guarantee has been processed. There's always the potential for lag and whatnot. Some of the benefits of logical replication are that you can run on different architectures, cross versions. You can replicate a subset of database changes, like if you only care about specific tables, or you have temporary tables that you don't need replicated. Those are things that you can basically target specifics of what you want, and the database clusters or the individual database nodes are themselves full databases. You can create other databases. You can, make tables, do whatever else you need to do on. Basically, it's only affecting the table itself. Some of the limitations, though, of logical replication are the need to specify the exact replication. You have to, itemize all tables that are involved. New tables are not automatically added. It requires planning. A lot of times, if there's any changes to like DDL for existing replicated tables, there needs to be special handling or maintenance for that, where you have to kind of coordinate the actual application of those scripts on there. And since there is a separate daemon to process and handle this, that's of course another moving part. More things to manage, more things that could potentially break. So that's that. Like I said, we're going to be looking specifically now at some different logical replication systems. We'll be looking at Sloaney and Picardo 4 and Picardo 5, which is in beta. So a quick overview here. As far as master-slave replication, you can see all three support that. We've got multi-master with Picardo 4 and 5 with more than 2 in Picardo 5 coming. It doesn't matter as far as conflict resolution for Sloaney, since there's no potential for conflict, but that's as part of the master-master resolution. And we've got some other features. We'll actually be covering them, so I'm not going to go fully into them here. But fundamentally about Sloaney, Sloaney is itself basically a distributed serialized event system. Its internals are stored in a Sloaney schema in each node's database, which contains all the support functions, triggers, et cetera, needed to manage things at the database level, with the Sloan daemon running for each node, listening and processing the events as they are processed. We usually interface with Sloaney with the Sloanic tool, and that's kind of how you will manage those things. Looking more in depth here, Sloaney nodes. The Sloaney node itself corresponds to a specific logical database instance that can be on different clusters, the same cluster, whatnot. It's basically has its own set of events that it generates and handles. So from each node's perspective, it sees all the other nodes in the cluster and can see what events the other nodes have been able to process. Each node has its own unique ID within the cluster, and I give information here about the tables, specific tables that it's stored in. And yeah, so that's basically all I'll say about the nodes there. Paths within Sloaney are connection information between any two nodes in the cluster. So the connections are only made if there's a defined listener, so you can generally define those for all. Basically, if you have n nodes, provide n by n connection information there, so you have the ability to reshape your cluster at future point and not have to worry about providing that information later. And that's basically just a DSN connection string. So you have node ID 1, node ID 2. It just tells each daemon how to contact the other database to get the information it needs. That's stored in the SL path table, and the create path is the Sloanic command there. Sloaney listeners are themselves the actual topology of the cluster that's basically saying which nodes care about events from which other nodes. Stored in SL listen table with create listen. And Sloaney sets, those are basically groups of tables or sequences which are replicated together. Each table, or each set itself, has an origin node, which is kind of the master, so to speak, for that set, and that's the only one on which you can make changes. You can have, within a Sloaney cluster itself, you can have multiple sets. The sets themselves do not need to have the same master, so you could have, one set of tables on one database that is, a specific master on one and one on the other, and that's fine. It doesn't care. It's able to manage that and propagate those events. Replicated tables are in the SL table. Replication sets are defined in the SL set table. Each table can only be within one replication set. You'll generally want to group any related tables together in a single replication set. For instance, if you have foreign keys or formal relationships, or if you have user triggers that do audit tables or something where you need to transfer data that should also be carried with it, you want those all to be in the same replication set. The subscription itself is basically how data itself is managed. The Sloaney subscription is basically a mapping of sets to nodes, and it kind of will define how the tables are able to pull, or basically how the nodes get their data. If a node subscribed to a set, it will receive data changes related to that set, and you have to be a listener in order to be a subscriber. So that's useful when you're defining the topology. One nice feature about Sloaney, which I really appreciate, is the cascaded subscription ability, which basically you can define a more complex topology for your cluster, so you don't have to have a single master replicating to a number of different slaves directly. You can have it replicate to a particular slave, and then that slave itself is able to replicate to other slaves within the cluster. It makes for very nice features, and I have an example that I'll go over later that covers this. One thing with the cascaded subscription is if you're going to be subscribed to something that potentially is providing to others, you need to just use the forward option for the data, which passes on all of the specific log data for any of the rows that are changed for that. A little bit of information here about the Sloaney triggers. When a table is added to the replication set, Sloaney installs the log or deny triggers to the table. What this is, these are the triggers that will track what changes are made and what is ultimately stored in like the SL log 1, SL log 2 tables. When the node is actually subscribed to a set for the first time, it actually has to copy the data over, so it'll truncate the table on the receiver side and copy that over. And Sloaney does this in order to ensure basically that it's the only one that ever touches the data, so it's able to guarantee that it has the complete data that's been unmodified, and is basically it is very careful about making sure that it's the only one that has any access to data. So a little more about the triggers here. Sloaney basically takes over the ownership of any of the track tables. On an origin node, it'll add the log triggers, which will fire after any DML change. That stores the information about the row affected, the primary key, the actual tuple data, the current snapshot, and this is all used to replay the actual changes. The subscriber node itself, they have deny access triggers, which basically means that without being the Sloaney daemon and turning those off, you're not able to modify the data, which sometimes seems annoying, but actually makes a lot of sense. Prevents any change to any of the table data, accidental or otherwise, and basically ensures that Sloaney is the only one that's able to change those data. As far as the actual changes, the Sloan daemon basically listens for a sync event and gathers event data from the provider node, since the last applied sync event is able to kind of take any of the log changes and figure out what it needs to do to get that table to the same state, and provides an event confirmation on the other node. So basically that remote node will know what's going on and where the state of that node is. It's inherently serial process, and so basically sometimes you can run into issues where a specific event is having trouble processing, particularly if you've gone around the Sloaney system and try to do things yourself. Don't recommend it. So that's pretty much Sloaney there. In depth here, we have a little bit of time to look at Picardo itself. We'll start out. It's a standalone replication system. I don't know how many of you are familiar with it, have worked with it, but one of the new features with Picardo 5 is the ability to transcend just Postgres. It can use other database systems as targets. It's trigger-based, asynchronous. Current versions, you can have a master with any number of slaves, dual master, and in the future, we support any number of masters, which will be nice. A little history about Picardo itself. It started at backcountry.com, written by Endpoint here, back in the Postgres 7.2 days. A little more history here. I don't think that's really that important. But yes, we have new features that are being developed with Picardo 5. It's in beta. Some of the strengths here, Picardo has low requirements. Postgres 8.3, Perl, a few Perl modules. Requires no changes to Postgres for its configuration, so kind of just slip in. There's a single daemon that it runs. You can basically have it anywhere that it can connect to all the databases in question. It's fast and it tolerates bad networks, has easy monitoring setup, etc. One difference here between Sloaney and Picardo, which can be a strength, is that the slaves are not locked, which means that you are actually able to change data on the other end, which, depending on your needs, may be useful. It's configurable. It allows you to have custom code, conflict resolution. There's different target types, and of course, it supports multi-master, which is nice. Let's see. This feels like a repeat. Anyway, but no, it's tolerant of network failures. If something breaks, it'll just log it and try again. So it makes it real handy if there are flaky issues. It's something that's not too terribly fragile. You can basically work off of like a PG dump instead of having to do a full subscribe. So sometimes that can come in handy if you need a copy of the database. You just want to start tracking changes. It makes it easy to work with that. It does not have like an automatic DDL handling like anything, because Postgres itself currently does not have triggers for system tables to detect those changes. But it'll handle many table modifications without reconfiguration. So if you add a data field to a table that needs to be replicated and just restart the sync, it'll be able to pick that up and not need to reconfigure anything. Some limitations about Picardo is, of course, it doesn't handle the DDL automatically. There's no formal failover within Picardo. It kind of considers that outside of its reach. So if you have a multi-master system and one of the masters goes down, it's basically up to you to determine, we just need to write to the other master. There's no delta replication, which is basically the trigger capturing without primary keys. It does support full copy for tables that do not have primary keys, but at this day and age, everything should have a primary key anyway. Also a limitation, also a strength. Targets are not locked, so they're still writable. It depends on your perspective here. But as far as guaranteeing, that all nodes are going to be identical, that's something that Picardo does not enforce. The daemon itself does not run on Windows, but databases themselves can. And one thing that it is annoying about it for sure is the bloat that gets involved with all the triggers. Right now you need external cron jobs to help vacuum and clean up the delta tables. In Picardo 5, it's actually incorporated in there, which it should have been a long time ago. A little more here about Picardo 5. The code's been overhauled. Everything's faster. There's no distinction between whether it's a master-master or master-slave. Uses asynchronous calls. There's as many masters as you want with different targets to other databases. Fairly boring technical details there, but basically it's able to use a lot more of the more modern features of Postgres. Unlog tables for tracking data and whatnot. Some of the use cases for Picardo where that might be particularly useful are distributing the read load, scaling, having redundant master servers, data warehousing, data reporting. Those two in particular because Picardo has the ability to have what are known as custom selects, where it'll be providing, instead of like the effect of select star from a table, you can provide any select for certain things, and so you can use that to transform data in the target database. You can use it to upgrade between Postgres versions, so get somebody off of one of these old unsupported versions and get it moved up to a more modern version. You can use it to join the NoSQL craze, just using the target database type MongoDB. And if you do have something that needs a big application that's kind of in the process of getting migrated, for example, with Oracle or something, you can continue to have that old applications database updated while still upgrading and moving things over. So yeah, like I said, as far as data sources itself for Picardo, right now it's just Postgres, though there's work underway for using Oracle or MySQL as far as capturing changes. A lot of this is, of course, volunteer, open source sort of work, so it's something that we don't know what else is out there that people need and whether that supports those functionalities. Targets for basically Picardo 5 here, there's Postgres, there's Flatfile, MongoDB, SQLite, MySQL, Oracle, Drizzle, et cetera, et cetera. Basically, we can probably get it to talk to anything as we need. So a little bit here more about Picardo. The terminology itself, unfortunately, we're stuck with the goat metaphor. Don't know where that started, and it's too late to turn back. But we have basically any replicatable object we call a goat. That can be a table or a sequence. Specifically, a herd is a group of goats. It's basically kind of like a replication set. A sink is, of course, a specification for what data will be replicated in what way. That will be, we want to copy from this database here to this group of databases here at this interval. It's basically able to provide kind of a specification for that. DB, just the database. And delta triggers are the triggers that are captured, basically capture any of the changes that are made to tables, so it's very similar to Sloaney's log triggers. Some requirements here, pretty much already covered those, I believe. It's fairly basic there. The Picardo architecture itself, daemon-wise, you have basically a single master control process that forks off different controller processes, which themselves are basically responsible for the individual syncs. Each controller process kind of monitors what are known as the KID processes, another nod to the goat metaphor. The KIDs themselves will do the actual synchronization and whatnot. It's kind of a three-tiered design here. Picardo control itself is the main user interface to the Picardo system that performs all control-related actions, all modifications to sync modifications, new tables, anything like that, and communicates with the running Picardo daemon as needed. All of the meta information, so to speak, about the database is stored in a special Picardo database itself, which Picardo control will connect to as it needs to. It keeps track basically of the full configuration for the cluster, all of the syncs, what tables are replicated, et cetera, et cetera. That's created for you when you run the install first. Let's see, this is going slower than I thought, sorry. We basically already covered what the goats were. Different sync types that Picardo offers. Picardo 4, you have the swap sync, which basically is the master-master. Each table has its own set of delta triggers, and then it's able to resolve those. Push delta is when one side of the table has a single set of delta triggers, captures it, and then it's able to push to unmodified tables on the other end. And then the full copy sync basically just zaps a table and copies everything over. Okay, the multi-master itself, we've kind of covered fairly well so far, but the dual master is the version supported by Postgres 4. Postgres 5 adds the true multi-master, is of course the swap sync, and uses database triggers to capture changes on the tables in question. When processing a sync, swap sync itself, there's the possibility of conflicts where both sides have changed the same row, and Picardo needs to figure out basically what do you want to do in that case. And that's where we run into kind of the conflict handling. Obviously, you want only one set of changes to persist, so conflicts are bad. We need to figure that out. So there's some standard conflicts resolution sources, some standard conflict resolution methods, either a source, specific source, a specific target, random or the latest, or you can always write your own version. I don't know why you'd want random, but in any case, that's a necessary part of any kind of master scenario. In Picardo 5, the multi-master will support true multi-master, meaning more than two. It should be able to support any number, and that's able to use a round-robin algorithm to kind of basically perpetuate the changes along. So. A little bit more about Picardo's master-slave. It's similar to Sloaney and Londiste in principle. That's the push delta sync. It logs the individual primary keys for rows which are inserted, updated, or deleted. The Picardo daemon notices these changes and replays it on the slave databases. Some of the differences here with the master-slave handling. The slave is not read-only. The primary key only of the delta row is stored, not the serialized row or value. And when changes are propagated over to the slave, use the current value for the referenced row, not the value at the time the event was logged. So essentially what that means is that you're batching up all of the changes between sync runs for a specific row. If you have multiple changes to the same row, it's only going to have one indication that the row itself has changed, compared to with Sloaney, multiple changes will result in multiple log rows, which is just a difference in design. Touched on briefly the custom selects. Basically, this is something that lets you change for a specific sync how data is going to be populated on the target. You can use this for data aggregation, normalization, transformation. For example, if you want to replicate only part of a table, specific columns, you can change the select to just do particular fields there. You can create summary reports and do that in the target, normalize, denormalize data. It's very powerful, very flexible feature. It's kind of Swiss Army knife, since you can make any select the actual target. I'm going to go now here to some side-by-side comparisons of Sloaney and Picardo, kind of showing the equivalencies and looking at things. For constructing the actual cluster itself, you usually will init that with Sloaney with the Sloanic script init cluster. We've touched on defining the individual nodes, but they have their ID. You create the nodes, you create the paths, you create the topology with the listen, and it will go ahead and initialize the database for you with the specific cluster schema with all of the information. Similar with Picardo, you basically set it up via the install. You add the databases. You can have what are known as DB groups, which are if you want to have, if you have 50 read-only servers, you can put them all as one database group and then set up a sync between the database groups. So similar as far as just defining basic topology there. For the replication itself, you define the set. Of course, Sloaney, we covered this somewhat. You create the set, you add the tables or the sequences to it. Similar with Picardo, you define your herds, provide the syntax for adding those. And of course, this will be more useful if you download these slides later. I'm not going to go over it right now. Some differences here in how the changes to the data are logged, the DML logging differences. The changes in Sloaney, of course, are logged per transaction. It logs the whole data for the whole tuple as it exists, and so multiple changes end up with multiple entries in the log table, which makes sense as far as Sloaney's design. And with Picardo, we're only logging the primary key fields, and we don't differentiate between the type of change, whether it's an insert, update, or delete. Yeah.
Slowly does not log the whole change row, only the change fields actually.
Okay.
Which if you have wide database rows with very large toasted fields and you don't update them, they will not be replicated.
Okay, great. I'll update the slides. Thank you. Row values itself at the type of the event are irrelevant. So basically, Picardo just notes, hey, this row is different than it was before. And then when it syncs, it deletes the row with the primary key on the target and inserts the current value of the row if it still exists. So it actually doesn't need to distinguish between any event type there. Multiple changes don't matter and they're not logged, so final state only. Basically, this only really matters if you look at, let's say there's a long period of disconnection where there's a huge number of changes on the database that haven't yet been replicated. With Sloaney, you'll have kind of a huge event log backup, which will take a little while to replay. With Picardo, it'll only matter for one per row that's changed. If you make a whole bunch of database changes, it'll pull the final value across, basically, as it replicates. Yep.
May I point out a drawback at this point? Because, first of all, this method, how Picardo replicates, is much more similar to how ER server worked as compared to how Sloaney and Londis work. And the drawback here is, with all these replication systems, you can have replica side triggers that fire and do things like auditing and logging of individual changes. With Picardo, you only get the snapshot at some point in time, not the individual changes. So that auditing cannot happen anymore on the replica. You must do that kind of auditing on the master.
That makes sense. Okay. Yeah. So that's effectively, that's one of the reasons why Sloaney stores it per transaction. Okay. Yeah, the type of scenario that this came out of was more kind of let's get the final value of this table pushed out. So yeah, different design modifications or motivations. But yeah, no, it definitely makes sense. That's good to know. Thank you. We look here at how you modify replicated tables, specifically DDL changes. With Sloaney, you can create a SQL script to make the DDL change in question and use their execute script functionality to apply it to the cluster. And that's done in such a way that it will ensure that any changes that are made or to the data, like let's say you make a change to a table that is replicated, you add a new column, it will ensure that if you then insert data into the new structure, because it has to process that event before it processes the new sync events, it'll make sure it has the correct table structure. So that's one of the nice things about the serialization and event design that Sloaney has there. With Picardo, you can either stop replication, perform the DDL changes on the affected databases in general, and then restart the replication. It's kind of annoying. It's definitely not an automatic process. You can also, if it's just a simple column addition or removal, you can apply the change first to the slaves and then the master, since it just does the select star by default to get the data. Once you make the change on the master itself, it'll start trying to push that column over to the slaves. And so you want to make sure the slaves have that column before the master does. Otherwise, it'll just be broken until you get it fixed. But yeah, in general, it's easier to just go ahead and start and restart.
When you have in Picardo, when you doing table update and you have some view in the master and you're hitting, for example, column, how it will be behaving? This data which was updated before you modified
As long as you're changing one of the data columns and not one of the primary key columns, it shouldn't be an issue. You'll want to make sure that the table itself, you changed on the slave first. If it's an addition. If it's a removal, you can remove it from the master first, and then it'll just be copying over a reduced set of columns to the target.
So if it's in master, you will have extra column and you remove the column, whatever records in the queue is, will be that column will not replicate it.
Since it just stores the primary keys for the affected rows for changes, it'll once the table structure changes, it will just, as it's processing those, it'll copy the new set of columns from the master, if that makes sense. I'm not sure. Do you feel like that answers your question? Okay. We'll talk a little bit about failover. Of course, Sloaney has formal failover, which is very nice. You can move a replication set, which basically means you're changing the node that the master is considered on within the Sloaney cluster. Sloaney, of course, goes through great machinations to make sure that everything is set up and the log triggers are changed and everything works well. One problem is if the actual node itself completely goes down, you have to use the failover, which is more forcible. It contacts all other nodes in the cluster and basically tells it to remove the old node, and it's not able to, basically you have to end up resubscribing that node if it comes back. With Picardo itself, there's no formal failover. If you do have, let's say, a dual master scenario, whichever node you're writing to will still collect changes, and if it ever comes back, it'll just replay and use the standard conflict resolution for any of the changes itself. Monitoring-wise, Sloaney has the SL status view, which shows the status of all other nodes relative to that specific node. Displays number of events it's logged or lagged by. If there's any lag time, that can be very useful to get something into Nagios checking on how your cluster's doing. Picardo has Picardo control status itself, which will show all syncs, any lag, and various statistics just about what's going on. So that's something comparative for monitoring. And as far as kind of going back to the basic idea here, what logical replication system do we use? There's no right answer. Different scenarios cater to different strengths. And I'm going to cover some real-life examples, assuming I don't want to run too late. I guess I'm doing good. For this case here, oh yeah, go ahead.
Can I just request that you show one custom conflict resolution example of Picardo for me?
Yeah, I don't think I actually have a slide here for it. So, okay. We have here an example, custom Picardo migration that we did here, where a client had a Sloaney Postgres 8.2 with 4 nodes, and they wanted to migrate to a 9.0 hot standby streaming replication cluster, and they wanted this migration done without app downtime, annoying clients. This actually ended up, since we used Picardo, this simultaneously had 3 forms of replication working, and it worked like a champ. It's kind of fun. So basically, a little more information here. They were running Postgres 8.2 with Sloaney on 4 nodes in one data center. Using Picardo, we ended up being able to keep downtime in minutes. It didn't matter what the size of the actual database itself. What we ended up doing, first of all, you end up create your new cluster, set that up. I think there were 4 nodes in that particular setup. Set up that as just a basic install with the streaming replication, hot standby setup for all nodes. Create a new cluster on an alternate port for the Picardo database because we didn't want to actually replicate that to the other nodes. And since the hot standby streaming replication migrates the entire cluster, we just decided it would be easier to run that on an alternate port. So we set the remote access up. This is probably a little more detailed than I needed to be. Basically set up a local install of Picardo using the alternate port. Created the structures, basically the schema on the hot standby cluster using PG dump all and schema only. We went ahead and we added connection information for the alternate location, and basically added a sink that copied everything over and started collecting the deltas for the table itself as it was going. Ended up pushing everything over. So basically, you end up using Picardo to kind of catch up the replication as the data itself, as changes are made to the live system that they had, they were pushed over. We got to the point where we finally were testing, and we just basically had to switch over the application to point at the new cluster and let Picardo finish propagating any of the changes from the old system. And once we verified that was all working, we removed Picardo from the old cluster. One of the ways this was nice was because we didn't actually have to change anything on the new cluster. There was nothing related to Picardo on the new cluster. It was just a target database, which it was able to write to and update. So worked out well for us. Case study 2 here. We had a data center migration that was a decent-sized database, had a Sloaney cluster, and we had a very high-cost link, very slow VPN. Effectively, we didn't want to have to create a whole bunch of new clusters or new Sloaney nodes on the alternate side. So we were able to basically set up a cascaded cluster. So a single replication stream was going over the VPN, and we just had to essentially replicate that once. Effectively, we just chose one of the nodes in the new data center. I think there were 4 as well, to be kind of the local master, so to speak. It was the provider. It received all the events and the initial subscription of the data set, which it took something like 12 hours to copy the data over. We actually ran into some TCP timeout issues that were silent because the hardware itself was causing issues. Not fun. We were able to set that up, and then the slow subscribe was limited to 1. The other nodes in the cluster were fast, relatively speaking. They were on, much faster connection, so the initial subscribe for those took a lot less time. And there was only a single stream of events that was going over the VPN itself for the live cluster. Once we verified that everything was working, we were able to do a move set to change the origin, which doesn't generate any more traffic than normal events. And we were able to verify that. And then once testing was going on, we were able to just drop the old nodes from the cluster, and everything worked great. So a little more information here just about Sloaney. It's their website, mailing list. It's actually not a valid email address. Sloaney1general@sloaney.info. IRC channel and whatnot. Again, you can probably find that online real easily. There are, of course, some other logical replication systems that we didn't look at, like Londeast or Tungsten, Ruby Rep, a bunch of others. That's basically it. Do we have any other questions?
So it seems like with multi-master replication, the scary thing is always the possibility that your masters will disagree, that they'll end up in different states.
Mm-hmm.
So I was wondering if you could explain how Picardo specifically avoids that.
Basically, when you're queuing up the changes, you have to pull. Effectively, you don't know that there's a conflict until Picardo is able to check in and say, okay, let's get the changes and try to resolve those. So it boils down to the to the conflict handling. So first it has to detect that there are conflicts, and then depending on the configuration, it's able to maintain those. So let's say there's the latest example. So if there's a timestamp kind of associated with the change itself, it's able to say we're just going to take the latest version of this row for which there's a conflict, and then it'll be able to resolve that, make the change on the non-winning master to be able to kind of get things resolved that way. Also goes back to, you were asking about an example of kind of the custom code conflict there. Basically, you'll be provided information about the row itself, and so you have kind of I don't know if it has to be in Perl, but I know that we can do it in Perl as far as being able to determine programmatically what the final value of the row should be, and that's what the change and ultimately ends up being.
So let's say you're in the worst possible scenario, that you have a conflict, and then one or both of the servers go down before you can run the code to resolve the conflict. When you come back up, will it automatically notice that and run the conflict resolution code?
Yeah, if one of the servers goes down during replication or during the sync, you'll actually have to restart that since it will not have noted that it was able to successfully handle things. So it's not going to lose the change, of course, unless you lose the database at all.
So Bucardo 5 is still, each server is still checking with every other server.
It
updates.
uses kind of a round robin approach. So basically, server 1 will compare server 2 with 3 with 1, or however many nodes you have in there. I'm not, Greg Sabino-Mullane is another endpointer, and he's actually done the majority of the work on the Bucardo 5 multi-master portion. So I'm not 100% sure on how that works as far as, cascading conflicts or handling or whatnot.
Okay. I guess my other question sort of related to that conflict resolution is, how do you avoid race conditions in conflict resolution in a high transaction database?
You mean as far as when you're processing a sync, how you prevent further changes, or how you prevent the row from changing itself?
Right, well, conflict
Underneath.
resolution is still going on, yes.
Yeah, well, what it does is when it processes the sync itself, it actually takes a serializable transaction on each side of the database. So it basically ensures that the changes to the tables in question are consistent throughout the Bucardo sync processing that it's doing right at that moment. So if something changes, it will be recording the additional change in the delta tables, and then at a later sync processing time, we'll have to resolve that later itself, if that makes sense.
Okay.
Yeah. Any other questions? When's lunch? All right, well, thanks, guys. It's great to talk to you.